Hi, my name is Garrett McNeil. I am going to be going over today my implementation of control reinforcement learning. I conducted this implementation as part of an RIU at the University of Louisville in 2026. So thanks to them. And I'm going to walk you through just some quick background knowledge. It's on my poster about how this works. And then I will show you my Google Colab notebook. This isn't really like a coding tutorial where I'm going to build it as we go, but this is kind of just a brief overview of what I've done. I will try to linger around some of the more crucial code parts so you can kind of get an understanding and an idea of why I made the choices I did, and also how you could possibly implement this yourself. So, the first thing you might be asking me is, what is control reinforcement learning? Control reinforcement learning makes use of sparse autoencoders in reinforcement learning, specifically the algorithm proximal policy optimization, or more widely known as PPO. And its objective is to improve the explainability of a network, but it also has a side effect where it can actually tweak and improve the performance of an LLM on a specific task. And it's really cool because it can improve the performance without changing the network parameters. So you can kind of change the behavior of your LLM without having to actually make permanent changes to its weights. So, next two questions you might be asking is, what is a sparse autoencoder and what is PPO, if you don't know. So, quick answer for PPO, reinforcement learning. It's a reinforcement learning algorithm. I'm not going to go over it too in depth because I want to keep this video scoped pretty reasonably, but there's a ton of tutorials online for proximal policy optimization, and I would really recommend you to walk through one or two of those if you want to implement this. It's going to be very helpful to be familiar with that and to understand why PPO makes the decisions it does, because that will help you be able to troubleshoot and be able to interpret your agent's performance and training in case things are going wrong. So the second part of the question is, what's a sparse autoencoder, is what I will go over here, because that is kind of the idea that this technique really sprung off of. And if you've already been reading my bullet points, you can see. So neurons in these networks are typically polysemantic. So what a polysemantic neuron means is that the neuron represents multiple ideas at once. Let's say I have a neuron that represents the color blue, the animal cats, and the game basketball. What a sparse autoencoder does is it decomposes these activations so that we can get more monosemantic features. So the sparse autoencoder would then try to decode that neuron and its activations so we get a separate feature for both blue, cats, and basketball. This is really helpful in explainability because when the neurons are polysemantic, we can't really be sure what the activation really represents, but sparse autoencoders help overcome that problem. Now, what sparse autoencoders don't do is they don't reveal which neurons change model output. You have to remember, they only are revealing which neurons get fired off and activated, and which features then are activated in the forward pass of the model at a given layer. But it doesn't really tell us which features are the most influential in a model's output and which features can really steer that model's output. So that's where the intuition of using reinforcement learning comes in. Reinforcement learners are really, really good at exploiting and maximizing the reward function to try and get the most cumulative reward over time. And so reinforcement learners are really good at identifying which features are actually the most relevant to change a model's output to better perform on a said task. So that's kind of what sparse autoencoders do, and that's kind of how we use CRL. So if you see down here, these bullet points, that's what it says. So this leads to some pretty fun intuition. So this basically says that as long as you have a model and you have a way to inject in the model's forward pass with a sparse autoencoder, so you might need to train a sparse autoencoder on the model's layers, but if you have a way to stop the model's forward pass in the middle, use a sparse autoencoder on the residual stream to extract your feature activations, then you can train a reinforcement learner to select a certain feature that you might want to activate, re-decompose that to go back inside the model's forward pass, let it continue generating its token, and ideally that chosen feature will steer the activation in the desired way. The desired way is indicated by the reward function, right? So reinforcement learners' whole signal of how good or bad they're doing in their world is all based off of the reward function. So in our case, I chose to train my agent on the legal bench dataset. It's a pretty difficult dataset, so it provides a really good benchmark for these smaller models because we have a lot of room for improvement and a lot of really difficult challenges to overcome. I specifically, this summer, I only researched with the Learns Hands task. That was because they're binary yes or no questions, which makes it pretty easy to automate the reward. I started this research as an exploration. I was fortunate enough to actually take it all the way to experiment and get results. And that brings me to the second point, or the last thing you really need for CRL, which is you need a way to automate the grading of the LLM's responses. You're going to need to run the LLM a decent amount and like grade each step to train it. So hand grading them is it can be done, but it's a pretty slow process, and I really recommend you to find a way to automate the grading of your LLM's responses on your given task if you're wanting to implement this on one of your own. So my research did conclude that CRL identifies subsets of features that are semantically meaningful and related to the task it's trained on. In our case, that was legal task. Specifically, the Learn Hands task ask and prompt the LLM to identify yes or no if there exists a legal issue within the context of a user prompt. For some more details, my model that I use in this, got words in my mouth. The model that I used in this experiment was a Gemma 2 billion parameter version. I use a 16,000 width sparse autoencoder, which means there's about 16,000 features there to choose from each layer. And then I only chose the top k=1 features, which we'll get to a little later. And my reward function was +1 for a correct answer, is 0 for an incorrect answer, and I use constrained decoding. So basically, I restricted the model's output tokens to only be yes or no to prevent the model from accidentally answering with white space. This is because I did use a non-instruction tuned version of Gemma 2 2B, which is used in the original paper, which is where a lot of my decisions were based off of. So I hope that kind of gives you it's a fire hose of information about sparse autoencoders. But here we go. We have a few more just methodology. You can see, hopefully this graph makes things a little clearer for you and exactly how this works. So we have our tokens bed. And this is kind of where our sparse autoencoder activations will change how the model works. You can also see it out here. So we have this generated output. And if you see here, when we amplified the features, let's say we chose the French feature and we amplified it, then it is able to steal the model's output. Here, for all my reinforcement learning people, is a bit more the formalization of our experiment. The state of our agent is considered its residual stream at its intervention layer. The action is a binary selection for which features it amplifies. Typically, we do this in a top K manner. I chose k=1, like the original paper did, for improved explainability. Our forward pass is going to be our transition function, and our reward is going to be, as I explained earlier. So I know it's a lot of information. There's a lot of theory and graph here. If you want an idea of where we could possibly go, you can pause the video here because here's my conclusions and future work. There's still a lot of exploration to be done with this methodology. Sorry, I'm getting all my words jumbled. But yeah, I would then like to really take you into the meat of this video, which will be the Google Colab notebook right here. So this is really where a lot of the learning information is going to be and how we can walk through and really do this ourselves. So here's all of the libraries I use. I believe I trained these. I actually used the T4s. I don't think I used the A100s for most of them. I used them at the end because I was running out of time with the program and needed a bit quicker results. So I have some general operating systems. We have our Torch neural nets. We have some analyzation libraries. And then here's where the LLM models and our data sets kind of come from. Cool. So I do set a seed. Not everything is completely seeded here, which is an improvement I can make on the experiment. Here we connect to our Google Drive. So this will let us analyze the agent's behavior. So actually, I'll show you that here and how that worked for me. As we can see here, I ran a bunch of different tests, and you're able to kind of do this with this setup. You just mount your drive, you create your string for your directory, and then you just kind of assert that exists. But as you can see here, we can provide some detailed logs about our training procedure this way. My question results are just kind of like CSV files where we can always refer back to the model's performance, the question number, the task subset, selected feature, and the critic values, so we can analyze our critic values. Critics can be used to identify bottlenecks, so that is pretty important. Then we also generate a results.txt for the entire training section, where we print out these checkpoint results. So you can see how it kind of improves, or not improves, depending on which run you're looking at over time. You can see which features it selects. But yeah, then moving on from that, here's just again, this is some boilerplate setups. We're loading in our models, we're loading in our tokenizers, setting our devices, setting our tokens. I recommend using user data. It's accessing Hugging Face. Here we load our sparse autoencoder. Here is where the constrained coding really comes into play, and where we only allow it to do the yes and no tokens. Down here, I like to store these total features and model dimension variables, because we'll pass them in later to some neural nets, and those will kind of help define our dimensions. If you're curious about how to pull data sets, a lot of this is just, if you've worked with LLMs in the capacity before, this should seem pretty familiar to you, so that's why I'm kind of skimming through it right now. It's not the most important stuff, but we're just pulling our data sets, and we're pulling our tasks that we're going to use to train the model. I guess it is worth mentioning, for if you're kind of questioning what I did, the Legal Hands dataset is split in a train and test technically, but most of the questions are in a task. The train sets are actually mainly used as example sets to inject into your prompt. So the model kind of has an idea of what that legal issue might look like. So we load our data sets. I load them in dictionary so we can have some intuitive access later down the line. I shuffle the data sets. That way we can get a train, validate, and test split. All right, so our first kind of like agent, right, in this setup is our actor agent. So proximal policy optimization makes use of both an actor and a critic agent. The actor's agent's job is to take in the state and output your action. So it's not really concerned about much else. And these are both implemented as kind of very small neural nets. They don't have to be super complex. This is pretty similar architecture to the original paper for control reinforcement learning. So as you can see here, we're not doing anything super fancy. We do pass in the dimensions of our residual stream and our sparse autoencoder. And you can see here, it's a little more clear. Our actor takes in the residual stream, passes it through its network, and outputs the sparse autoencoder. That will then turn those into a log probability, and depending on training and test, either sample or take the max. So you can see here why I wanted to grab these guys over here, some variables, because we might be passing those through later. And then our critic network is pretty similar, but it's even simpler actually. So we do take in the residual stream, but our critic is only outputting one value, and this is the value function of the current state we're in. For those who maybe you're watching this before you go through some reinforcement learning, the value state is pretty much, it's like an estimation of how good the state is going to be, and it's based off of how much cumulative reward the critic thinks that the agent can earn in that state. So for simplification, you can kind of think of it as a sense of good and bad right now. It's very simplified for the meaning of the value function, but yeah. So that's why we only output one there as opposed to the actor where we're outputting the entire features. So adaptive feature masking is an idea that the paper mentioned, and this kind of gets into one of the first problems that we have to solve. So reinforcement learning agents typically like to explore their environment. They like to walk around, they like to push things, figure out what's going on before they really start to converge on a policy. If you notice from earlier, our width of our sparse autoencoder is 16,000. So that means there are 16,000 actions that our reinforcement learner can take, and we do not train for 16,000 steps. So that obviously presents a problem. How do we keep the reinforcement learner from pretty much perpetually exploring its environment in like a reasonable training session? Adaptive feature masking kind of limits that action space by masking out options in the actor's logits. So what it does is, in the original paper, how they implemented it was it started off as a complete empty mask, right? No features were technically on. And then as the agent got questions, when the feature got activated in a forward pass, it would be turned on in the mask and it would become available for the actor to select. I chose to implement it a little bit differently. I reset the mask every forward pass. That was just my implementation choice in detail. This is another area where it's not like a super concrete right or wrong way to do it. But I do recommend that you implement adaptive feature masking in some way or another. Otherwise, your agent is going to have a really difficult time exploring your environment and your action space. This is just a helper function to get labeled activations in a format. When we pass through the sparse autoencoder, it's going to get a lot of zeros and a lot of garbage activations. So we want to pair this in a more readable way where we get the index and the value. The value is important because sometimes, depending on your implementation, you want to store the magnitude of the value, and you might even want to use that to calculate some other things, like your steering coefficient, which is just kind of like how strong you amplify your selected feature. So we have all these like kind of parts. We have like an actor, we have a critic, we have a sparse autoencoder. And I chose to tie all of these together in a CRL controller class. It's basically just kind of a little organization that helps me interface with everything kind of at one spot and keep track of all my pieces. We are also able to set a lot of our hyperparameters here, and kind of communicating during these hooks and these forward passes gets pretty simple when we do it like this. So this is where a lot of the information will be. But yeah, our sparse autoencoder like isn't like technically an agent. It's technically like a function, but I threw it in with them. Our optimizers for our neural nets, we have some hyperparameters. These are entropy if we are using entropy, and a clip E is a hyperparameter in a PPO algorithm. A smaller clip E means that your agent is going to be kind of more cautious. Typically, you want it to be between 0 and 1. 0.2 is recommended. Higher clip E's means your agent's going to be a little more reckless and it's going to be not as afraid to like explore wildly new options as it goes. Our learned variables. So this is where our steering coefficient comes into place, right? The steering coefficient in the paper was sampled from correctly predicted outputs. I chose to just set it as a constant that the paper verified to be a pretty good constant at the layer I was using. Your steering coefficient can drastically differ the behavior of your agent, so it is a hyperparameter you can play with. I am starting at layer 20. 50 is a pretty good coefficient according to the original paper at layer 20. So that is why I chose that. And then we have our mask for our features. Yeah, I also should mention that layer 20 is actually chosen for a reason, not just at random. Typically, later in the model's forward passes, we can get kind of like broader ideas. In the model's earlier passes, they found that like it was focused more on organizational information, and then later it was focused more on like the kind of like broad like human concepts. We have a memory buffer here. This is going to help us store our information for our training updates that we'll do later. And then we have some self-tracking here to report some graphs that you can also save to the Google Drive that I showed you earlier to help analyze your training process. And then these are used by some of our later blocks of code to kind of get some information about what happened during the injection. We just have a few wrapper functions to set our flags, get our mask. This is just a function to generate a graph based off of its history. Here is a train function. I will go over that, but first I think it's more helpful to go over the steer function instead. So if we're not steering when we return, obviously, we have to do a little bit of pre-processing of our steering data. Then we come down here. Again, if we're not training, then we don't really want to keep track of what's going on with our nets, so we turn off the torch grad. This is just, to not keep unnecessary information, and we're not always training, we do evaluate, so this is definitely important, comes into play. We get our value from our critic, which we'll use to store in last critic estimation and our memory buffer later. That comes more into play during our training update, but as you can see here, we can really start to see how this works. And I will show you exactly where this function gets called. We set it as an injection inside of our hook wrapper, which is right after this class. So if you're kind of lost and you're wondering, like, where does this logic execute, don't worry, we will go over that in a second. Just kind of focus on the initial logic of our steer function will take in a residual stream. It will perform the activations, it will ask the actor to select a feature, and then it will return the recomposed residual stream from the sparse autoencoder. So here is where we get said sparse autoencoder activations, right? It's just as simple. The sparse autoencoder takes our squeezed residual stream, and it'll input activations, and then we use that helper function we defined earlier to clean our activations, so we get an array of tuples where it's the activation index feature. So it's like, if I chose feature 5 for basketball, right, this would say 5, and the magnitude might be like 8.47. Then we reset our mask. This is, again, unique to my implementation. You can implement this in whichever way you feel, but I do recommend implementing it in some way. Then we set our flags for our mask and our activation. We make our logits, and we are going to set these small value. That way when we soft max, anything that is maxed out is going to be pretty much 0. We get our log probabilities, and then right here. And then if we are training, then we want to sample. This encourages our agent to explore options that might not be most optimal. That's more of a reinforcement learning idea where you want to balance exploration and exploitation. You want to make sure you're trying everything out, but you also want to make sure that you can exploit the best option to gain the most reward. And then if we're not, I choose to argmax. I did run some experiments where we just didn't argmax, and even during evaluation, we sampled from the distribution, and I think performance declined a little bit, but that also might be task specific. So that's just another example of another part of this process where you can kind of toy with your own approaches. There's kind of not one super right way to do it. Again, this is a pretty new concept. I didn't see any other papers on the archive about this when I implemented it. So there's a lot of tinkering that is kind of up to your delegation. Last feature selection, again, we set this flag for some later functions. We get the log probability, which we're going to want to use in our training update later. We get the decoder weights of all the features. We apply our perturbation right here with this logic, get the state, and then here is what we append to our memory buffer that we will use in training later. We do training in batches in PPO, and actually, real quick, I will show you the last line right here. Then we return our residual stream plus our perturbation. So basically, all in all, what this does is it takes that residual stream, asks our agents, hey, what do you think of this? What's our feature we should select? It does some math based on the flags we set, trying to change its behavior, and then it returns the modified residual stream to the transformers forward network. I hope that was understandable for you. Then, if we come up here to our training, I won't go as in depth to this. I will just kind of let you pause the video and look at it if you wanted to replicate. But this is a standard PPO training update. We do batch training, so we do things a lot of the time batch size is one of our hyperparameters that we define later in the notebook. So that will kind of adjust how many episodes we update at once. We want to kind of update in batches because if we don't, then what's going to happen is the model is going to overfit to the recent training examples, something that I definitely encountered during my summer exploration. As you see here, we just grab our states, our features, grab all the information we need for our algorithms. Critical loss is a bit simpler. I'll just kind of let you look over here. Like I said, as much as I would love to go over the proximal policy optimization logic with you, it's just a little out of scope of what we're doing today. And I would really recommend you to go find a great tutorial online and follow that. But just so you can see my code, so you have transparency of everything I did, here's also my actor update. And yeah, so that is kind of the class. Again, it's not like super complicated, and I think you might have noticed already, it's very lightweight in terms of how big these neural nets are. And these, like, when I say like agent, right, these aren't like LLMs, or these aren't anything I'm like querying. These are just small neural nets running inside of a class. So then, once we have our agent, wraps on nicely a little CRL controller, we have a hook wrapper. A hook wrapper, pretty much all it's doing is it is taking in a function and it is letting you, like you see here, modification callback. I chose to implement it like this in my notebook just because the idea of interjecting in a sparse autoencoder, or with a sparse autoencoder at a certain layer, like, doesn't have to be constrained to like how I implemented CRL. So this hook wrapper lets you actually choose any function as long as it takes in visual stream and returns it back for the network's forward pass. So again, like there, I'm not going to go over too much in detail here, but yeah. Here's where we define our objects in our memory so we can actually use them, get our actor, critic, and our controllers. We set the modification function for our interceptor. And this block right here, I want to highlight to you because this is a super important block. This is actually where the interjection happens. So if you don't do this, no logic will execute. So when I told you earlier about that steer function, where it gets executed, you can see here, we define our controller. Then we tell our interceptor to set the modification to this controller steer function. And then in our hook handle, oops, accidentally clicked the run button. It's going to probably throw me an error for variables. Oh, no, it's going to try and connect first. We can disconnect. That is okay. Yes. But yeah. We set the layer that we want to interject at. We register our forward hook function to be the interceptor hook's residual stream function. So just kind of some semantics, but these semantics make this more modular and it makes it capable of adapting to however you want to approach this problem. Here's just some of our experimental setup. So here's my recommended helper functions that kind of help me analyze the results of the agent's training loop. So I use a confusion matrix. This was mainly because I was dealing with binary yes or no answers. This is one of the most intuitive ways to analyze that kind of data. Again, if you've worked with machine learning or LLMs or anything, some of this is probably not new information, so I'm not going to go over it in a lot of depth, but I will show you all the pieces that I use to help build this. Right here is just a print function. If you notice, in a lot of my print functions, I do two things. I both print the output, so you see I create an output string and I print it, but I also return it. This is what allows us to get these big text files, and those strings I'm pretty much appending on each other to generate these logs of the agent's training. All right, so this is again another analyzing. We take our selection feature, we just take the top K features. You can see here, that is this bit right here. Training evaluation, this kind of gives us a look at how well it did. So if you can see down here, when we return, we get correct answers, accuracy, feature selection, question results, etc. These are kind of the inputs that will pass on to those other wrapper features or wrapper functions I was just showing you. And these are needed to get all of our output strings. Here we have our test results. Again, you can see this kind of lines up right here. So we gather our results, and then we, based on our samples, the model we're using in our agent. And actually, if you see here, sorry, I should have gone a little more in detail here. Now I'm realizing this training eval actually samples is the number of questions it's evaluating on. The model is our LLM, the CRL agent, self-explainable, and then seed is just for some reproducibility about which questions it selects. And this will actually, sorry, I should have specified this a little bit better. This will actually take you through a test loop. That way you can just call this function in your code, and you'll see it down later. And then this evaluates that test run. So this is typically, I use this while I'm training to get some benchmarks about how it's going for the agent, and I also use it at the end on a bigger training sample set or a bigger test sample set to kind of get an idea of its overall performance. All right, next we have our checkpoint function. So something I experience is these things can fail in the middle. I think we typically train for about 4,000 steps, 4,000 questions, but it can, depending on which GPU you're using, take between an hour to 3 to 4 hours. So it is very helpful to use these checkpoint functions. This also lets you load the different networks. So like what I did is I trained a bunch of different agents with some different hyperparameters, and I use these checkpointing functions to save their behavior, save their networks, and be able to reload them and test them on larger sets later when I was done training everybody. Here is prompt directory, excuse me. So this is manually more specific to the task I was using. Legal Bench, like I said earlier, it kind of lets you prompt these models with some train questions. This is where I got those questions, but if you're wanting to use prompting to enhance your model anyways, this is a really simple way. You can just create a directory, create your text file prompts, and load them like this, so you can use them later. Here's the hyperparameters for our experiment. So as I told you earlier, our training episodes, our batch size, how large our network updates are. 64 is a good starting point. You might want to go, I would recommend going in multiples, so then go to like 128 if you want to up it. This is how many times we passed over that. Again, you might want this to be a bit higher if this batch size is a little lower. This is how many times we iterate over those examples in one training episode. Our eval, sample size, periods, and these are kind of starting to get a little self-explainable. Again, if you worked with this, I would hope that these variables are feeling familiar. Here's our checkpoint directory where we're going to actually store all of our models and our results. Cool. And so here's the training loop. So thanks for sticking with me this long. We finally made it to the training loop and got past all the prerequisite setup and knowledge. But again, it's not too crazy. We make sure our steering is active. And then for each training episode, select our task, get our sample, we get the prompt ready. And as you can see, it's actually pretty simple because all we have to do is tell our model to generate an output. And then when we get our token ID, decode it. And this is because all of that logic that I just showed you lives inside of that steering function and that training function. So actually, when it comes to training this on different tasks, on training this on anything you want it to, that's why I wanted to show you the notebook. All you have to do is really take that CRL class and that hook injector class and a model, and you're kind of just running for the gates at that point. You just need a way to evaluate your model's output, which we do right here. So again, just we're checking the tokens and the outputs. If it's correct, great. If it's not, then oh no. Again, we're setting our advantage. This is something in the PPL loop that we need to do. We set it in -1, I believe, earlier. So, and then if we're evaluating, again, this helps us print that evaluation. We get our results string. We save it to our results file. and then we save the evaluation episode like as a CSV. That way we can go back. Again, I'm a big advocate for just saving your results as you go. That way, if you realize you didn't get something you want, you can go back and always run some Pandas scripts on it to get it. And then if we're updating, here's our update logic. Again, I'm not going to step through every line of code. If you need to see it, feel free to pause the video. Hopefully I'll also link this notebook in my description. Then again, same thing with the checkpointing. At the very end, we just do one last save, and then we save our graph. So that's kind of the whole process, and I just repeated this experiment a few times with different hyperparameters. There's a little bit more. This is an optional block. This is an example of how you can kind of reload and retest on a wider set. So you can see I implemented it. Just my models were the directory that the network parameters were saved in. And I looped through all of those directories so I could test each of those models. And then I tested them 3 times, 3 different seeds. And I kind of went through a similar process of grading and storing results. Again, I'm just going to kind of linger here. That way, if you want to pause the video and look at it, you can definitely do that. Hopefully the notebook will also be linked. This was a bit long of a video. Apologize if I was talking fast. There's a lot of information here, but I just wanted to share this out with anybody who's looking to replicate this or see anyone else's work on this issue. I'm an undergraduate student. I'm by no means a world expert. But this was the work I did at an RIU over the summer, and I hope that this could help you, whatever your task is, whether it's implementing it on your own personal LLM for your own task, or whether you're hoping to maybe further this research. I think there's a lot of areas we can improve on. We can improve, actually, I've already written this down, and I will show you in my conclusions and future work. So, different learning rates, or again, just hyperparameter adjustment. I explored a little bit, but I didn't get to really thoroughly explore a wide set of hyperparameters. Different methods, again, different tasks, expanding it more on LegalBench. If you have your own benchmark task you would like to try this out on, there was only a handful that the original paper did, so there's still tons of benchmarks that haven't been tested across this task. Cross-task performance, using multi-objective RL is something that I think could be really fruitful with this. I also believe that the original paper experimented with doing this kind of intervention at every layer at once. Again, you can read my bullet points. I don't have to read it all for you, but I really hope you've enjoyed my video. I hope you've learned something. I hope you've kind of gotten something out of this, and I hope you have a good day.